Doug Terry's down in the Silicon Valley lab, and he's going to tell you about the replication protocol for WinFS. This actually represents kind of a continuation of work that he's been doing for probably 10 years now, since we worked on this kind of stuff that's around Spark for a system called Bayou. And now it's finally getting into something real with WinFS.
Exactly, hopefully. Yep. Okay, so this is about WinFS. I assume all of you have at least heard some talks on WinFS. WinFS is the new storage system going into Longhorn, which is the next version of Windows. So there's a lot of interesting innovation going on in WinFS. This is just one small, well, let me take out the word small. This is one piece of WinFS, namely the replication protocol. I've been working with the WinFS team over in Building 35 for the last 9 months, commuting up here regularly from Silicon Valley. And so I'm going to tell you about the piece of WinFS that I've been most involved with. I want to acknowledge the people I've worked with. So as I said, this is part of WinFS. This work is done in the WinFS synchronization and caching team. And the people that I work most closely with there are Irina Hudis, who's the head of the team. She's the product unit manager for WinFS Sync. And Lev Novak is the main architect. But there's also a lot of other people in that group that I work with. I want to especially acknowledge Irina and Lev, partly because I took some of their slides for this talk. I also want to emphasize that this is not a research talk. This is a talk about work we're doing in a product group. And so that has certain ramifications. In particular, I want to emphasize that you shouldn't go out and tell all your friends about the great stuff you're going to hear about today, because this is really stuff that we're not talking about externally. In particular, Microsoft is in the process of filing some patents on some of this technology, and any early disclosure would hinder that, aside from also the issues of disclosing product information before Microsoft is willing to do that. So please be, maybe more careful than usual with the material that you hear today. So what am I going to tell you about that you can't talk to other people about? First thing I'm going to do is tell you about the goals and requirements we had for this replication protocol, this platform that we're developing. I'm going to tell you the basic concepts involved in replication, change units, versions, knowledge, how the protocol goes about propagating updates between replicas, and what we do about conflicts, and how we detect them and resolve them. And then that should be about an hour today, hopefully this morning. And then this afternoon, for those of you who are diehards and really want to hear more, I'm giving a follow-on talk where I talk about some of the additional issues like filtered sync and metadata cleanup. And I'll be upfront about the problems that we haven't solved yet that I could use your help on. So what's the overall goal here of replication? The idea behind WinFS is you've got, a bunch of what they call items that are grouped into folders, and so you might have a collection of Word documents or PowerPoint presentations that you want to share with people. You may have your collection of photos that you've taken with your digital camera that you want to share with family members. So somehow you have this folder of information, and you would like to share it by replicating it to different places. And so there's this concept of a logical concept of a shared folder, and that shared folder now may be replicated on any number of replicas. Here I show 4. And we want to keep those replicas in sync for some definition of in sync, and that's the goal of the replication process. These replicas may be well-connected replicas within what's known as a castle environment, some home environment where you have a relatively high-speed network connecting them. They may be replicas that exist on someone's laptop that's only occasionally connected. They may be replicas that are widely distributed across the world. And so there's a whole spectrum of topologies and underlying environments that we have to be able to deal with. And so if you look at the requirements placed on this synchronization protocol, they're actually quite large because WinFS, maybe not necessarily in the Longhorn time frame, but eventually is going to be the underlying storage system for all of Microsoft's applications. And so we had to take a broad spectrum of applications requirements into consideration in designing the replication aspects of the protocol. And when I first looked at this long list of requirements, I thought, oh my gosh, these guys are never going to do this. I don't know of any research projects, any research replication papers or anything that you can go to and say they meet all these requirements. And so that's what made it interesting for me as a researcher to get involved, but it also what makes it scary as a product. So the main requirements here are, one is they want to support multi-master updates, meaning anybody can update any replica, okay, without locking or anything. We want to be able to support peer-to-peer topologies, meaning that replicas are just peers of each other. There's no main master server that's controlling the replication process. Recall that Longhorn is a client release, and so there's no actual server as far as Microsoft is concerned here. This is software that people go and buy and install on their PCs, and they have to be able to talk to each other and replicate among themselves without any sort of master control. We have to deal with WinFS schemas because that's the system we're dealing with. So that means that we can take advantage of the WinFS schema definitions in some sense, and I'll tell you that in a minute. But it also means that we have to be able to support WinFS schema. So we're not simply doing database table level replication. We're replicating at the level of WinFS items. We need to be flexible about configuring what and when to sync. We need to deal with conflicts. We need to handle varying network characteristics. As I said a minute ago, some replicas may be intermittently connected, some may be well connected. We have to deal with the whole spectrum. And because this is a client release, because it's software that people go and buy and they install in their home machines themselves, they don't have system administrators, we have to make sure that the system works right out of the box. We can't have a lot of configuration parameters that people have to set up. So there have to be reasonable defaults. And we have to guarantee that eventually the replicas converge, meaning there's some reasonable definition of consistency here, even in these environments where things are unmanaged and people have configured their systems differently. Okay. So, by the way, you should feel free to ask questions at any time. So the basic high-level approach we took is it's a read anywhere, update anywhere model, meaning if you can get to any replica, you can update that replica, you can read that replica. Without, as I said, without locking, without doing anything else, without talking to any other replicas. And that's important if you have a disconnected laptop. You can just do whatever you want on your disconnected laptop. And now the basic protocol is a pairwise reconciliation protocol between replicas. Two replicas get together and they say, here's the data I have. Let's bring our databases into sync. And so everything I'm going to show you is a pairwise protocol, very similar to what we used in Bayou, and similar to what Active Directory uses. The topology and the schedule for when replicas get together and what replicas get together is defined by the application or the users in the situation. For the most part, we don't care as long as there is a well-defined schedule and as long as the topology of who syncs with who is eventually well connected. You don't have groups of people who are disconnected syncing. Yeah, Mike?
Is it defined by the users in conflict with the just works out of the box without having to touch it?
You might think so. No. So what I meant by that is it can be defined by the user, but there are default configurations right out of the box. So for instance, in the castle scenario, the default configuration is that the castle already knows to find other machines in the home environment. It will just set up a sync schedule that talk to everybody. Perhaps the most interesting decision in terms of that affects the rest of the system is that we use a net change approach, meaning there's no update log maintained in the system. What we do is we take the databases that exist at those replicas, we add a little bit of metadata to that data, and we use that metadata to drive the replication process. That's the only thing you have to drive replication is the actual data that is stored in WinFS. And that has some advantages and it has some major consequences, as you'll see. There's also an adapter architecture for WinFS machines talking to other non-WinFS machines, like if you want to get information out of Exchange or Hotmail or Active Directory. I'm not going to talk about that today. For what I'm talking about today is the protocol for WinFS to WinFS replication. Okay. For the most part, you don't really need to know anything about the WinFS schema to understand this protocol. But there are a couple of places where the WinFS schema affects the replication process, and I thought I should point those out. In WinFS, the entities that are objects that are stored by WinFS are called items. So think of an item as things like an email message, a PowerPoint presentation, a Word document, a person's contact information. Those are all items. Each item in WinFS has a schema that says this item consists of a number of elements. So like for contact information, an element might be a person's email address, and another element might be the person's home phone number. Okay? And that's basically all you need to understand about WinFS at this point. Yes?
Is it possible for elements to be other items?
Is it possible for elements to be other? It's possible, no, not as defined, but it's possible for there to be relationships between items. So you can have links between items. For the most part, for replication, we ignore those links. The only kind of link that we care about for replication is what elements belong to an item, and an element is in a single item. It's owned by that item. Yes?
Restriction that an element or an item can't be opened for update during replication?
There are certain locking issues that if the item is open and there's a transaction in process, it may be that the replication process can't get in there and read it. That's the only restriction. For the most part, today I'm going to ignore that issue.
So an element, for example, if it were a PowerPoint presentation, just trying to wrap my head around this, would it be a chunk of the data file, or would that be more like, one of the entries?
Well, there are schemas being defined for all of these different types of things, and I don't know what the current details of each of those schemas are. And like I said, you don't need to know for this talk either. In fact, for the rest of this talk, I'm going to assume that items consist of a single element, just for simplicity. But before I do that, let me tell you the technical distinction as far as the replication protocol is concerned. So an item is the granularity of consistency. And what I mean by that is if someone goes in and does a bunch of changes to an item, to different elements of an item, the replication protocol will guarantee that all of those changes get sent atomically to the other side, to the other replicas during replication. But that's the only unit of consistency. At the application level, an application can open a transaction, update a bunch of WinFS items, commit that transaction, which causes all of those items to be atomically updated. But then the replication process comes along, and it doesn't know about those transaction boundaries. So it does not maintain it does not maintain the transaction boundaries across items.
So doesn't that give you very strange semantics with regard to transactions?
It gives you no semantics with regard to transactions as far as replication is concerned, yes.
Okay, so let me rephrase. Doesn't it greatly reduce the utility of transactions?
That's an interesting question. Our clients, which are basically all of the applications in Microsoft, seem to think that they can deal with that.
Well, right now they're writing on to NTFS that doesn't have any transactional data at all.
Right.
But
So I think it's an interesting question, and I don't have the answer to that. In particular, I think it comes up if you say we want to take all of the not the existing sort of Office applications which don't deal with transactions well currently, but if you want to take the applications that run on SQL transaction replication, let's say, and we want to move them to WinFS replication, now we have a problem, and we don't have a solution to that at this point.
imagine something like an Office application like Outlook, where you take an item and you move it from one folder to another within Outlook, and you really want that to be atomic. You
would like that to be atomic, and we don't guarantee it. I mean, but it's okay because eventually you'll see both of them. But if your sync gets interrupted in the middle, you may be left in some weird state temporarily. Yeah, and that's a consequence. Okay, so that's an item. An item is granularity of consistency. There's no larger consistency unit. There's a change unit, which is smaller than an item. And the change unit you can think of as an individual element of the item, though it could be subfields of that element in some cases. It's defined in the WinFS schema what the change units are for each type of item. And the change unit is, first of all, it's the granularity of update. So when you come in and change an item, you don't have to overwrite the whole item. You can just overwrite individual change units. So I can change the email address, for instance, of a contact. And the data at the database level, it tracks that level of changes. It says, oh, I know that the email address changed. And the reason it's important to know that just the email address changed is because the change unit is also the granularity of propagation. So when two replicas get together, I don't have to send the whole contact information. I can just send the changed email address. And Perhaps more importantly, the change unit is also the granularity of conflict detection. So if the email address of a person changes at one replica and their home phone number changes at another replica, the system won't detect those as conflicting updates. It will simply merge those two updates together into the item. Okay, but having said that, as I said, from now on, you can pretty much ignore the distinction between items and elements and change units, and I'm just going to, for simplicity, the rest of this talk, assume that each item is a single element. Okay, so the next thing we have to worry about are versions. So each change, each update applied to an item or an element has a version attached to it by the system. And the version is a two-part version. It consists of the ID of the replica that made that change, the replica on which that change was first applied, not the replica that received the change via replication, and some local counter at that replica. So you can think of the counter as just being the account of the number of updates that this replica has performed. And so a version is things like, I'll use A5, meaning this change was done by replica A, and it was the fifth update done by replica A. So A5 is the version of this change. B2 is a version, C7 is a version, and so on. So each change has a version, and that version sticks with that change as it propagates around the system via the replication process. The version of an item now, or particularly the version of a change unit, is the version of the last update applied to that item, or that change unit. And since updates totally overwrite a change unit, we know that the last version applied to that, the last change applied to that, is uniquely defines the contents of that change unit. And so that's the version of the change unit. Okay? These versions, I should point out, are not versions that are useful to users. WinFS at the user level has no notion of versioning. So users can't go in and say, give me this version of this item. Saying version A5 is not a useful concept to users. These are versions that are used solely under the covers for purposes of replication. And given two versions, A5 and B2, there's no a priori way of knowing which one came first, or if either of them came first. Did A5 come after B2 or before B2? So essentially, these versions are just unique identifiers for the changes. Okay, but they're important unique identifiers because they allow us to keep track of what changes a replica has seen. So the basic concept in WinFS is that each replica keeps track of the set of changes that it has seen locally. It doesn't keep track of anything that other replicas have seen. It maintains no state about other replicas. It only maintains what it knows itself. And that's the concept of knowledge. So the knowledge is a concise, I'll describe in a minute what concise means, description of the set of changes that this replica has seen. And now the basic protocol works as follows. When a replica goes to replicate with another replica, it says, here's my knowledge, this is what I know. The other replica then says, okay, given what you know, I'll enumerate my database, I'll find the changes in my database that you don't know about, and I'll send those to you. I'll send those to you along with the versions for them, and along with some other information that allows you to detect conflicts and allows you to know what you learned from the set of changes I sent to you. Yes?
Are the changes treated as tentative or as committed at the moment?
There's no notion of tentative or committed here.
Because there is no primary replicant.
Right. Changes are just changes. When you receive a change, you apply it locally.
So what happens during reconciliation of conflicts?
Pardon me?
What happens during conflicts?
What happens with conflicts? We'll talk about conflicts in a minute. Okay? Yes.
So how's this different from a virtual clock?
How is this different from a virtual clock?
Maintain causality, what I've seen from you.
Right. So we're having to do more than maintain causality here. We're using this to keep track of what you know. So a virtual clock allows you to, given two changes, tell the causality of them, perhaps. It gives you a total order on them, or a partial order, which. But this is more than causality. This is really figuring out what you're missing and trying to do that in a concise way. So in some sense, they're actually different concepts. There's a question back here. Yeah.
I'm curious to know if the size of the knowledge, basically, can it be linear in the
Okay, look at that. Good question. That's a perfect good question. That's the 2 slides.
So from your description, is this, when two replicas are dealing with each other, are they bidirectional or is it unidirectional?
It's the protocol, as I'm going to show you, is unidirectional. I'll have an example in a few minutes, so just hold on. Okay, so that's a good question about what's the size of knowledge. Before we understand the size of knowledge, we have to, I think it's useful to think about knowledge abstractly. So what are the, if I was going to write a C# class for knowledge, what are the main methods I need to have on knowledge? And then any representation of knowledge that provides these basic methods would suffice for the protocol. So given the high-level description of the protocol I just gave you, there are three main methods we need to be able to support. One is we need to be able to test if a given some knowledge, whether it includes some given change, some version. Okay, does this replica know about this version I have in my database? Second, we need to be able to add new versions to someone's knowledge because they learn things over time. And third, we need to be able to take the knowledge of two replicas and merge them together. I just did a sync with this replica. He sent me all of his changes, so therefore I know everything he knew. So we're going to take our two knowledges and we're going to merge them together, and that's my new knowledge. So any implementation of knowledge that meets these three methods would provide a correct working protocol. Now the interesting question is, what about the size? So the simplest implementation of knowledge would be, say, a knowledge is just a set of versions. That's the simplest one. You can do all of these operations on sets. But it has the unfortunate property that a set of versions grows indefinitely over time. So it wouldn't be a very concise representation of knowledge. It would be a very poor representation of knowledge, but it would give you a correct working protocol. Yes, Mike?
Versions with dates, I assume.
Pardon me?
A set of versions with dates.
Set of versions with what?
Dates.
I don't even need dates. I just need to know the versions. That's all I need. Why would I need dates? All I need to do is given a set of knowledge to be able to know whether this version is included in that. That's just set membership. Merging two sets together is easy. Adding a version to a set is easy.
You don't need to know with disjoint updates which is the most recent?
Well, so we're going to get to conflicts, but you will see that this protocol relies on no dates and no timestamps at all. Hold on. Yeah, the other question.
Is there an assumption that if you receive version AN, that you've received version AN minus 1?
No. There's no assumption of that either.
They're complete overwrites, so it doesn't matter.
If they're to the same item, they're complete overwrites, so it doesn't matter. Right? If they're to different items, then you can receive them in any order. Yes. So we can't make any assumptions about that, and that's what makes it tricky. But you can assume that reasonably, that in the usual case, you receive updates in the order in which they were done. And so that's what allows the particular knowledge implementation that we've adopted, and it's the version vector. This is the same knowledge representation that was used, for instance, in Bayou, and the same one that's used in Active Directory. And the notion of a version vector is that you have an entry in this vector for each replica, and it says, for this replica, I know all the versions up to this number. Okay, so I have a version vector that might be, if I have three replicas, X, Y, and Z, I might have a version vector that says X4, which means I know all the changes from X up to 4, all the changes from Y up to 3, and all the changes from Z up to 7. So this is a concise way of representing, I know X1, X2, X3, X4, and so on. The advantage of version vectors is that they don't grow over time. They're linear in the number of replicas, not the number of updates. Yes, Atul.
So this version vector associated, there is one version vector with each item?
No, there's one version vector for the whole replica.
Of the whole replica?
The whole replica has one version vector that says, this is the set of changes I know in this replica. Okay, so it's very small. So it's very concise. We have to deal now with the question of things arriving out of order. Things might arrive out of order. I might know, in this example, up to X4, but I don't know X5, and I got version X6. So I may occasionally have to have exceptions to this knowledge. And it says, I know this version vector, plus I know these other things that arrived out of order. But if things don't arrive out of order very often, these exception list doesn't grow, and we'll see that.
Why don't they arrive out of order?
If you make minimal assumptions about the transport. You can, for certain transports, guarantee that they don't arrive out of order, which is what we did in Bayou. One of the things about this WinFS protocol is in particular, the transport decision hasn't been made yet. And so we designed the protocol to make minimal assumptions about the transport. So,
Just to be clear, a replica is a replica of one of these folders.
A replica
it's not a whole disk worth of stuff.
it could be a whole WinFS volume worth of stuff, or it could be a particular individual folder. Yes.
Because if I assuming that you're normally going to get things in order, if you have them be really giant things, it might take a long time before you get all the updates.
You might. In which case, you may end up with some exceptions to your knowledge. But eventually, those holes will be filled in. Yeah. But you don't. The observation is you don't expect the exceptions to your knowledge to grow linear over time.
Right, because they get filled back in anyway.
Because they get filled back in. Right. Yeah. Question in the back.
So when a replica gets applied to, when something gets replicated, does it become a new enhancement? Does it become a new enhancement on the local one that it's being applied to, or does it carry the original number from the source?
It carries the original version. A change always carries the original version. It gets the change when it gets applied by the application to WinFS is assigned a version, and that version travels with that change. Is that the question?
I think so. Yeah.
It doesn't get reassigned a new version every time it gets applied at a replica. Yeah, Dave.
So when in that example you have, you're missing X5.
Yeah.
Suppose X5 becomes semi-permanently lost.
Yeah.
Do you end up seeing X6, X7, maybe?
Okay.
Will you compress the exception?
We'll compress it, yeah. So I think the next slide is an example of showing this. Because in particular, X5 may have been a version of something that was overwritten. And because we use state-based replication, I may never get X5. Because X5 was overwritten by Z7, let's say. So we have to deal with that problem. So that's the other reason you get holes. Okay, so here's a convenient example to show you the protocol. So here I have two replicas, machine A and machine B. In this example, machine A is replicating from machine B. As I said, it's a one-way protocol. If you want to do two-way replication, you just turn the protocol around and run it the other way. Each replica has 4 items, I through L at the top. The thing in green is the version associated with that item in their database. So machine A has version A4 for item I. Machine B has version C4. So they have different versions of this item, but at this point they don't know who has the most recent version or anything. I'm going to ignore conflicts in this for this example for right now.
Why does machine A not know the most recent information about L, or just the L is only changed at version 2?
Machine A, L was only changed by version A2.
Okay, and then at version A4 I got changed.
And then at version A4 I got changed, exactly. Right, so that's the other thing, is that these versions are assigned replica-wide, they're not per item. So the 5th update, the A4 was done to item I, whereas A2 was done to item L, and A3 may have been done to some other item. It may have been overwritten, it may have been done to I and overwritten by A4. It might have been done to J and overwritten by B3, we don't really know. Okay, so there's a set of items, there's one knowledge vector that describes the set of changes I've seen. And so in this case, as I said, each database has 4 items. The only other thing to point out in this example is that there's this little skull and crossbone next to K on machine B. That means that B actually deleted this item. So that's called a deletion tombstone. One of the things about state-based replication is that when you delete an item, you can't simply remove that item from your database because no one else then will find out that you deleted that item. So when you delete an item, you simply mark that it's been deleted. And so in this case, it was deleted by B, and it was B5 is assigned the version. So deletes, just like any other updates, are assigned versions. Yes?
Maybe you're missing a little something about your model. Does A4, say change A4, does that apply only to I? I mean, is it possible for a change at A, the 4th change in A, to apply to both I and K?
Oh, sorry, I didn't say that. No, each changed unit, each time a change unit is changed, it gets its own unique version. So I should have said that. So even if a whole bunch of change units were changed in the same transaction, each will be assigned a unique version. So one will get, if they were updated by replica A in some transaction and you had 3 changes, one might get A7, A8, A9 as the versions for those 3 changes.
But the GUID would be the same.
So the GUID, replica A, they were all done at replica A, but they all get unique versions. So each change is a modification to a particular change unit gets a unique version. Yeah, I should have said that.
So how big is the counter?
So how big is the counter? That's a good question. So we're I don't know what's the counter size, and make it 64 bits, and you're probably okay. I mean, it's no different than log sequence numbers in databases and stuff. Okay, so here's the example now. So when machine A wants to start talking to machine B, it says, I request changes from machine B, and he sends B his current knowledge vector. A4, B3, C6, D0 in this case. Machine B now goes through each item in his database, at least conceptually. In practice, he doesn't actually go through each item in his database, but in this example, we'll show it that way. So he looks at item I, and it says item I has version C4. Machine A knows up to C6. So he already knows this version. I don't need to send it to him. Then he goes and he looks at item J. Item J has version D2. Machine A doesn't know about D2, so I will send it to him. So I do a convey changes message, and I say, here, I'm sending you item J, and it has version D2. By the way, it also sends the contents for item J. I've ignored all the contents in these examples. I'm just showing you the metadata that gets sent. But clearly there's some important data that gets sent along with for item J as well. And there's a bundle ID, which I'll describe in a moment. So this is bundle 1. Okay, and so when machine A gets that, he takes the D2, he replaces his version of J with D2, and he's all happy. Again, I'm ignoring conflicts. I'm assuming no conflicts here. We'll do conflicts in a minute. Okay, and he adds D2 to his knowledge. At this point, he can't simply update his version vector to say that he knows D2 because he hasn't seen D1. So we have an exception in his knowledge at this point. And the reason he hasn't seen D1 is because D1 may have been overwritten by D2. It may be some later item in machine B's database that he's about to send him. There's lots of reasons he may not have received D1 at this point. He doesn't know. He doesn't care. All he knows is he has to add this exception to his knowledge. Okay, B keeps going. He says, I have this tombstone for item K. That's B5. You haven't seen B5, so I better send that to you. And at this point, machine A does the same thing. He takes B5, he replaces his version of K with that, and he says, now I know that K has also been deleted. So the only thing this affects is now that when machine A runs queries, he won't see K as a result of those queries.
Wasn't there just a conflict there?
There was just a conflict, but yes. The astute ones of you in the audience will realize that there was just a conflict, but we're ignoring conflicts now. I will use the exact same example when we talk about conflicts, and you'll see that, in fact, we should have detected a conflict at this point. Yes. Okay, so machine A now adds B5 to his knowledge. And at this point now, you see machine A knowledge is getting very fragmented. He's starting adding exceptions for everything that he's receiving. How do these things go away? They go away at the end when machine B is completely done enumerating his whole database, and he sent A everything he knows. Now machine B can go to A and says, here's the complete bundle message, and if you got all of these messages that I sent you, and you applied them, in particular if you got these 2 messages, and you applied them, then you now know everything that I know, and this is what I know. Yes?
For machine B, is there any relationship between the IJK version numbers and the knowledge vector?
Is there any relationship? Sure. I mean, the invariant that the system maintains is that every change that's been applied to your database, namely to these items I, J, K, and L, has to be reflected in your knowledge vector.
Then why are they different?
Why are they what different?
Like the values that B maintains, the knowledge vector and the IJK.
Because they're different because, you're saying, why is this B6, for instance, when there's no B6 there? Because B6 may have been overwritten by C4. B may have done an update to B6, and then replica C came along and overwrote that update, and B replicated with C and learned about C4 and overwrote B6. So you can't, in general, take the maximum of those and produce your knowledge vector. Your knowledge vector is what changes you've received, but some of those may have been overwritten in the process. Does that make sense?
Yeah.
So do you send a version number for every item at the end?
For every, you send a version at the end?
Right, that's A3, B6.
At the end, I just sent you my current knowledge. I sent you my current knowledge.
And that's per item or for the, is that the version?
For the whole replica.
It's per replica.
It's per replica. Remember, knowledge is per replica, at least at this point.
Okay.
So I just sent you my current knowledge. You now know, so conceptually, I told you everything I know, so you now know at least what I know.
Here we have,
go ahead.
Here we have like a duplicate, like 2 items for item like I, for example. So do they have to be in the same order? And what happens if you have several changes pertaining to the same item?
If I have several changes pertaining to the and they don't conflict, then I only send you the most recent change. So that's the advantage of state-based protocols over log-based protocols. There may have been lots of changes to item I, but I only send you the most recent change because that's all you need.
Do you do this but on machine A? Is this done rolled inside a transaction so it all happens atomically?
Yes. Otherwise it doesn't work.
Okay.
That's right. Well, I mean, you could commit the convey changes individually because now your knowledge is just fragmented. So
yeah, but if A is replicating off to C, if
this message gets lost, then it's okay because he just ends up with fragmented knowledge. He ends up with these exceptions in his knowledge.
Right, but what will happen is you'll wind up with fragmented knowledge expanding and not getting destroyed.
Well, yeah. So the bigger problem is if B is currently synchronizing with C and B is adding new items to his database and updating his knowledge vector, and then sends A knowledge of things that A never got sent, now you have a problem.
Yeah,
okay, so if B is doing concurrent synchronization, and B at this point uses an isolation, a snapshot level transaction when it enumerates its database to make sure that no updates happen and changes its knowledge that it sends to A.
Yep. Good.
Yep. Yeah, so that's the bigger problem. A can be syncing. The recipient side of the protocol can be receiving stuff concurrently, and you don't have a problem. It's only at this last step. No, it's not implied. That's the trouble. Because there's no way, if I don't have this last step, there's no way for A to know that he's never going to receive D1. Whereas B knows that he's never going to receive D1 because it's included in B's knowledge and he has no D1, so obviously it was overwritten by something that he has. And this is the way for B to tell A that you're never going to receive D1, so just go ahead and update your knowledge vector. Okay? Again, this is a consequence of state-based replication. If you have a log-based replication where you're guaranteed to see every version, then you don't need this. So, for instance, in Bayou, we never did this. But a consequence of state-based is you need to have some way of telling the person that he's missing some things that were overwritten. So at this point, when B gets this learned knowledge vector, he simply doesn't replace his knowledge vector with the one he learned from B because A knows some things that B doesn't know yet. So what he does is he takes this knowledge vector and he merges it in with his own knowledge vector. So he takes the maximum component on a pairwise, on a component-by-component basis to produce his new knowledge vector. So now he has more knowledge than B. And at this point, these exceptions go away because once you have an exception that's dominated by what's in the knowledge vector, you don't need the exception anymore. So at this point, we're back to a nice clean state. As I said, if the sync protocol got interrupted in the middle, it's okay. It would pick up next time where it got interrupted, but my knowledge wouldn't be as compact. That's the only problem there. Okay, so that's the basic protocol. There are some things here I didn't show you. We ignored conflict detection and resolution, which I'll get to in a minute. We've ignored batching. I showed you, each message going out as each individual update going out as a single message. Clearly, we're not going to do that in practice. You can batch these things together. And in fact, in practice, what you generally do is batch a whole bunch of conveyed messages with the learned knowledge message at the end so that they get that as one batch and apply it as a single atomic transaction at the other side. There's an interesting question of an open question that we can talk about this afternoon if you want. Of if you're doing batching and I send you a batch that's not the whole database, what can I send you as your learned knowledge? That's an interesting problem. There's some topology optimization they didn't talk about. There's filtering. So one of the things we want to support in WinFS Sync is not just replicate whole folders or whole WinFS volumes, but right now I want to get just the messages in my inbox from Bill Gates because I'm expecting an email from him. So just give me those. There's some interesting questions there. And there's an interesting question about how you do metadata cleanup. When, in particular, when can I remove all these tombstones that are cluttering my database? Again, I'm not going to. The filtering and metadata cleanup I'll talk about this afternoon for those of you that are interested. For the rest of today, I want to focus on conflict detection and resolution because that's an important part of the basic protocol. Question before we get there.
Seriously, what are you using to trigger for the replication? Is it just time-based, or are you looking for change that?
As far as the protocol is concerned, we don't care what triggers it, right? So what happens is people set up sync schedules. So they say, I'm going to sync, I'm replica A, I'm going to sync with replica B once an hour or once every 5 minutes. You could also say, I'm going to sync with replica B, every time I've done 100 updates. You can have it triggered by your update rate. You can have it triggered by lots of things. So currently, I think in WinFS, it's all time-based schedules.
The replicas don't have to be a fully connected.
Right. The topology can be arbitrary. A can sync with B, B can sync with C, and A and C never talk to each other directly. That's right.
So I had a question about state-based changes that you're sending. So initially in Farsight, we actually had state-based changes going from the client to the server, and we were forced to change it to a log-based changes.
Yes.
And the primary reason we had to go for that was security and sort of implicit ACL changes.
Sure.
Right. So we were worried that basically that the operations that happen on the client side, the server needs to be able to verify them. However, if we send just the state, the server could not verify whether those changes were really valid or not. I can show you an example offline.
Yeah, let's talk about that then, because in WinFS the ACLs are associated with items. So if I'm sending you the changes for an item, I can at that point detect whether or not you are allowed to read that or write that.
But do you have nested items? Do you have items, nested items or things inside items which have different ACL properties than
so it depends upon your ACL model. Yeah,
okay.
Yeah.
So we should
talk about that. Yes, the head of the chief security architect for WinFS also happens to be Lev Novak, who's the chief architect for WinFS Sync. So that we have some hope of getting those two to right. Okay, so let's talk about conflicts. So first of all, what is a conflict? We said, one of the consequences of having this model where updates can happen anywhere is that two replicas may inject updates that conflict. And what does it mean for an update to conflict? There are two types. It means that the semantics of those changes are incompatible, and there are two ways in which they may be incompatible. The most common one in WinFS is that two people updated the same change unit. Two people went in and changed someone's email address or their phone number or whatever. Those changes are incompatible. The other types are there's some constraint-based conflicts. The most obvious of those in WinFS is that you can't have two items in a folder with the same name. So it's the typical file system-based constraint. And so if two people create files and they both happen to put them in the same folder and assign them the same name, then that's also going to be detected as a conflict. I'm going to ignore that kind of conflict for right now and just talk about the overlap-based conflicts. And the second property that you need for a conflict is that these changes were done concurrently. It's okay to have, two changes to the same change unit if they were done sequentially, meaning they were done with knowledge of each other. But if they were done concurrently, then it's a conflict. Okay, so now we need to, as I've told you so far, or the protocol I presented so far, we don't have enough information in our metadata to be able to detect conflicts. Version numbers are not enough to detect conflicts. And so what you need, at least conceptually, is you need something called made with knowledge. And now here is where I'm going to temporarily violate this statement that knowledge is only per replica and not per item. And then I'll go back at the end of the talk and tell you why that's not actually true. But for purposes of explaining it, think of knowledge, made with knowledge, as knowledge associated with each item or each change unit. And the made with knowledge is the knowledge that the replica had at the time that this change was applied. So essentially, it's this change was made knowing all these other versions. Okay? And so now for each item in our database, or each change unit in our database, we have an ID for it, we have a version for it, and we have made with knowledge. The set of versions that this change knew about. And now we can detect, that's enough information to detect concurrent changes. So two changes, C1 and C2, are concurrent if and only if the version of C1 is not included in C2's made knowledge, and the version of C2 is not included in C1's made knowledge. Meaning they were made without knowledge of each other. That's what concurrent means, right? This allows us to detect that if we explicitly store all of this stuff and in the database and send it during update propagation. So let's look at the same example again now. We'll satisfy your conflict here. So now we have the same database. I removed the tombstone, however, and in addition to versions, we have made with knowledge associated with each database item. In addition to the base knowledge. Okay, the base knowledge still says, this is what I know. The made with knowledge says, this is what this item was made with. Okay, so the protocol works the same way. Basically, you request changes. Machine B goes through and enumerates things. A still knows about C4. A doesn't know about D2. I'm going to send him D2. But in addition to sending him item J with version D2, I'm going to send him the made with knowledge for that version. Okay, it was made with this knowledge. When A gets this made with knowledge, he looks at his current version of the database, B3, and he says, okay, B3 is included in this version's made with knowledge. Therefore, this version overwrote B3. There's no conflict here. I can go ahead and apply this update. Follow me? Okay, so he just goes and applies the update J2. And he adds it to his knowledge just like before. Machine B realizes he doesn't know B5. He sends B5 with B5's knowledge. And now here's where we have the problem. Okay, A's current version of this item for K says my version is C5. B sent him made with knowledge that only goes up to C4. Okay, so clearly B5 was made without knowledge of C5. And also C5 was made without knowledge of B5 because I don't know B5. He doesn't know B5. Okay, so the criteria of concurrent updates applies, and there are updates to the same item. So we have a conflict here. So at this point, we don't want A simply to take this update as it did before and overwrite its database. So instead, what it does is it puts it in its conflict log. So it says, okay, I have a conflict here. I'm just going to log the conflict. And so now version K, B5 of item K gets logged along with its made with knowledge as a conflict. So essentially, I have two items in my database with the item. I have two versions in my database of item K, one in the main database and one in the conflict log. The protocol proceeds as usual. I update my knowledge. I get my complete bundle. That overwrites and gives me back to a clean knowledge state. But now I'm left with this thing in my conflict log because I had a conflict. So right now I'm assuming that we do manual conflict resolution. Okay. So now this conflict stays in the conflict log until some user comes along and manually resolves it, or some application comes along and says, there's a conflict here. I'm going to do an update that resolves this conflict. Meaning I'm going to do a new write, and I want that write to be the current version of the item. Okay, so suppose some user on machine A or some application comes along and sees this conflict and produces a new update. Okay, so this new update gets assigned a new version. This update was done at machine A, so it gets assigned version A5, which is the next version that A hasn't used. And it gets assigned made with knowledge, which is A's current knowledge. And now, this made with knowledge includes both B5 and C5. So this overwrites both of these updates resolving the conflict. So at this point now, A5 goes, it replaces the K, it updates his knowledge, and the conflict goes away. The conflict was resolved by this manual operation. And that's it. That's how conflicts get resolved. And now what happens is anytime someone goes, and when machine A now replicates with other machines, it will send him version A5 of item K. So what's going to happen in practice is that this notion of the conflict log going away because this update has made with knowledge that overwrites both of the conflicting updates, that's going to happen at all the other replicas that log this conflict too. So any replica that realized this conflict, that logged the conflict, as soon as they receive A5, they will say, A5 was made with knowledge of this conflict and this guy, and so the conflict goes away, it resolves the conflict, and the conflict log gets cleaned up. So the fact that a user at one replica did manual resolution, this resolution now propagates via the normal protocol and cleans up all the conflict logs at all the other replicas.
But since you're doing this pairwise, if somebody else resolves the conflict,
But you can in fact have two users that see the conflict simultaneously and resolve it, or simultaneously for some definition of simultaneously, and resolve it concurrently and fight. That's a problem. And I suspect users aren't going to do that in practice, but it definitely can happen. But it's definitely a problem if you get to automatic conflict resolution, which I'll talk about in a minute. Yes.
What happens if, while you have a conflict in the conflict log, and before it's attended to by the user, he actually makes another version of K
yes.
on machine A?
Yes.
Does that generate a new conflict, or what happens?
No. So if he at the time that this is in the conflict log, let me back up. At this point, this guy can still go ahead and update version K. So he'll update version K. He can produce he can say, I'm just updating version K. And now he has to update it he updates it without knowledge of the conflict, though. And so his made with knowledge for that update will not include version D5.
Okay, so it just resolves the same way.
Right. And so you can keep going and updating your database copy while you have something in your conflict log, as long as the made with knowledge of that database copy doesn't say it was made with the conflict, because you haven't seen the conflict.
But now you really do need this made with knowledge rock for those ones.
Right. Yes, exactly. So you better be careful about how you maintain that made with knowledge. That's right. And then the same thing will happen, though. Eventually, when someone comes in and says, I'm resolving both of these, I know about both of the conflicts, I'm resolving it, it will go away. Yeah.
If two conflicting changes were made with the same knowledge but they're identical, do they conflict? Or?
Unfortunately, the answer is yes. There's some debate about whether they should, in fact, conflict.
Because this is a particular case where two applications are going to resolve it the same way.
If they resolve it in the same way, it sure would be nice if you just said those actually don't conflict, and we'll just go ahead and take the version. It's the same content, so we're just going to take that content and apply it. There are some problems with that, which we can talk about this afternoon if you want. Why that doesn't? That works in some situations. It doesn't work in all. So I've been claiming that we should, in fact, do that, though it doesn't solve all the problems. Yeah.
Assuming that all elements of an item are independent.
Yes, we're assuming right now that all elements of an item are independent. Again,
clients have had no problem with that.
Right. Again, there's no guarantee, there's no read-write dependencies across items or anything like that. Yep. We're assuming everything's independent, and our applications are fine with that. Yeah.
The conflict log is visible to applications through some explicit API.
There's an explicit API in WinFS that says, let me look at the conflict log, and there's also an explicit user interface. I believe it's going to use the existing syncman interface to allow you to look at conflicts.
So if these two guys mutually run the protocol, then they're both going to end up with this conflict on K, but they're going to have them in the other order. They're going to have them in the opposite order?
Well, potentially, yes. That's another interesting open question about whether, if we have multiple conflicting items, whether we should pick one to be the database item so that they at least see the same databases. Yeah. Some people claim that's not important, but I think it's a good idea.
Theoretically, we're going to end up with a very large vector of made with knowledge, right? Not this or limit.
We're going to end up with a large vector of... the vectors themselves are the same size because there are a number of replicas, but we end up with a vector per item, as I've described it here. So we end up with a lot more metadata. But that's the... I don't know that I'm going to have time to give you the argument for why we don't need that. Yeah.
If there are multiple change units on the same item, and one of them is a conflict, do the non-conflicting change units not get applied until the conflict is resolved?
No, since change units are all independent, any change units that aren't in conflict will be applied immediately.
But you said that consistency was on the item.
Consistency is, yeah. So that's the one place where. Good point. That's the one place where this notion of consistency being an item is actually violated, because if I do two changes to an item, one of those changes is to a change unit that conflicts, and the other one doesn't. The one that doesn't conflict will be applied, and the one that does conflict will be logged. That's absolutely true. Okay. So let's move on. Okay, so I showed you manual resolution. Automatic conflict resolution is also supported in the system, and it basically works the same way. instead of some user having to come along and resolve the conflict, at the time that a conflict is detected, there's some conflict handlers registered in the system that will get invoked. The conflict handler could say, I don't know how to deal with this kind of conflict. It's involving things that I don't know how to deal with, in which case, if none of the conflict handlers can deal with the conflict, it will just get logged, and we have the same situation I showed you before. If a conflict handler does know how to deal with a conflict, it produces a new update. That update then gets applied to the database, and no conflict ever gets logged. Okay, and then the results of that conflict handler propagate around in the usual process. So unlike some replication systems where they say we're going to run automatic conflict resolvers at every replica, and each replica is responsible for individually resolving the updates, the conflicts that they see, this is a different model. This says that the conflict resolver runs at a replica and its resolution propagates around. So in fact, we could have the problem, you say, where multiple conflict resolvers get invoked in parallel, and they produce then resolutions which conflict and ad infinitum. So that's an interesting problem that we have to solve. The typical scenario, though, what you would expect is that you got some updates. They're flowing. You got two conflicting updates. They're propagating around the system. Eventually, they hit a replica that discovers both of them. That replica invokes its automatic conflict resolver, resolves the conflict, and now the resolution propagates around, and the conflicts themselves stop propagating around. So in fact, you have this nice property that the first replica that sees it resolves a conflict, and now that resolution propagates around. You still could get scenarios where two replicas independently detect the conflict. It's actually surprisingly hard to come up with those scenarios, though.
Should you be forced to use the same conflict procedure, the resolution procedures? I mean, this is very confusing.
Well, so that's another, because we're in this unmanaged environment, we can't necessarily assume that all of the replicas have installed the same conflict handlers. Okay, so it would be nice if we could assume that everyone had the same conflict handlers.
Would you update them using your system?
Well, the conflict handlers are code, and people get really nervous about, automatically updating code and so on. And so the safest thing to do is just not assume that everyone has the same conflict handler. And even in that case, we still get convergence here, even if some replicas don't have. And so, for instance, you could configure the system so that you have a designated replica that resolves all conflicts, and it runs all the conflict handlers, and none of the replicas do any conflict handling at all. They just log them, and that would work just fine in the system.
But then you have to have somebody who understands this well enough to configure it.
Yes, absolutely.
You need connectivity to it.
Yeah.
Will there be any kind of a mechanism for automatic updating of the conflict handlers? Maybe on my network I want that.
That's an interesting question. I believe the answer in version 1 is no. There was a lot of debate about whether you want to do any sort of automatic updating of
Yeah, no, I understand the implication. But
So the simple answer is no. Yeah.
So is the conflict resolution invoked immediately, or do you sort of for instance, you could sort of say that you should first try to peer with other people and sort of check with other replicas, and then if the conflict persists, then...
No, the conflict resolution is done immediately.
Okay. Couldn't you sort of minimize this problem of multiple people independently resolving it by actually holding off, like doing a back off kind of thing?
That's an interesting idea. We hadn't thought about that. We should talk about that later. Currently the proposal is that as soon as the conflict is detected, it gets resolved, and we have some other mechanism for detecting that there are conflict resolvers fighting with each other.
Sounds scary too.
Yeah. Okay, so the second thing that's interesting is that there's a storage optimization. I told you that we're explicitly storing made with knowledge with each item because I think that's the way to conceptually think about how the system works. You can reason about the correctness of the system that way. But in fact, in practice, we don't actually have to store it unless there is a conflict. So the way to think about this is if I took my database and it has no conflicts, there's nothing in the conflict log, and I went and touched all the items in my database, they would all get updated versions, they would all get updated made with knowledge to be my current knowledge, though there still wouldn't be any conflicts. So why not just treat my current base knowledge as they're made with knowledge? Okay, that was a lot of hand waving. But that's the basic intuition behind why it works. And so in fact, I have a version of the protocol next which runs through the exact same scenario without using made with knowledge. I think in the interest of time, I won't show it to you, except let me just do real fast and show you that there's one tricky part, which is that when I actually detect the conflict, I have to maintain the made with knowledge on conflicting items, and C also better maintain his own made with knowledge. Okay, so at this point, only the items in conflict have made with knowledge. And getting back to your question then, if C gets updated, his made with knowledge gets updated, but nothing else.
But how did he create that made with knowledge? I mean, he didn't have it before and he saw the conflicts.
I took A's current knowledge and made it his made with knowledge without B. So I squirreled it away before I updated his knowledge to include B. So his made with knowledge was A's base vector plus D2. And that works just fine. Okay, and now the same thing works. As soon as we do the resolution, it goes away. And we're back to a clean state. Okay, I realize that was awfully fast. We can talk about that more this afternoon if you want. Okay, so that's the basic protocol with conflicts. Based on this version of knowledge, let me just summarize here by telling you the key features of the protocol. We're going over them again. So clearly, this is a protocol that favors availability over consistency. Right? If you want transactional consistency and all that, this doesn't give it to you. But it has the nice property is that you can work on disconnected laptops and you can update anywhere and you've got maximal availability. Anytime you have some data item, you can update it, you can read it. I think it's an interesting question about how to get consistency back into a protocol like this. Because the protocol has this property that replicas only know about their own changes. They don't keep state about other replicas. That's a very nice property to have because it makes the protocol very robust. If you think about the protocol, if messages get lost, if they get reordered, if sync sessions get terminated, the protocol still keeps working. Because you only update your local knowledge when you've actually got a change that you've applied, and you do it atomically with applying that change. So, in particular, we made minimal assumptions about the underlying transport. And this property also means that we can get pretty decent scalability, I believe. Unlike some replication protocols that try to keep track of what all the other replicas know, and then you get this n-squared state problem. Each replica's base knowledge is simply proportional to the number of replicas. So in particular, my goal here was to have a system that would scale to 5,000 replicas, which is about the size of the largest Active Directory system, as far as I understand. For 5,000 replicas, your knowledge has about 20 bytes per replica. So for 5,000 replicas, you're talking about 100 kilobytes. Exchanging 100 kilobytes at the beginning of each sync session is not unreasonable, even over a Wi-Fi connection or a DSL line. Yeah, Mike.
But in particular, that means that you can't have a directory which is replicated on every Microsoft employee's machines.
You can't have a directory that's replicated on every Microsoft employee if every Microsoft employee is going to update it. So that's the other observation, is the size of the version vectors is only the number of updates.
Okay.
So, for instance, one of the scenarios we have to support is this thing called the offline address book.
Yes.
The offline address book in Outlook is replicated on everybody's machine. So if you look at Microsoft, there's 100,000 copies of it or something, right? But no one updates it. It's updated centrally, so that's okay. So for the offline address book, we end up with a version vector that has one item in it.
Okay.
So how long do you have to keep tombstones around?
So you have to keep tombstones around. That's the metadata conversion update problem that we'll talk about this afternoon. But basically, the short answer is you keep them around until they're common knowledge.
You assume that the number of replicas is...
Until everybody knows about them. And then how you detect that. That's the hard part. Yes, that's the hard part. That's this afternoon. Okay, yes?
If I change address and phone number in a contact, are you going to make those changes atomically on the replica, or is it possible for me to see one and not the other?
If they're in the same item, as I said, that's what it means for the IWB consistency unit. I make those atomically at the replica. But if they're across items, all bets are off. Okay, so I think we succeeded in getting something that's reasonably scalable. It's efficient in terms of bandwidth because if you notice, it has a nice property that each update, each change is only sent at most once to each replica, independent of the topology of the system, because of the fact that each replica maintains its own knowledge. Independent of topology, independent of interrupted sync sessions or anything, you guarantee that each change is sent at most once. And some changes aren't sent ever. If they get overwritten, if you've got a hotspot in your database and something's continually overwritten, those intermediate changes will never be sent. So that's a nice property. And it's efficient in terms of storage because we don't have an update log that we're maintaining. All we have is this metadata attached to the existing database item. So we have this version metadata, and we have one knowledge vector, and that's basically it. As I said, we support arbitrary communication topology. Anybody can talk to anybody. If you want to build a hub and spoke topology, you can. If you want to do peer-to-peer, you can. If you want to have a master replica in which all the updates flow through, like the offline address book scenario, you can. It's pretty flexible in terms of that. The other interesting thing is if you do happen to have an underlying transport that supports multicast, for instance, I've shown it as a pair-to-pair protocol, pairwise protocol. But if you support multicast, there's nothing that prevents you from taking convey changes messages and putting them in multicasting them out to all your peers.
Maybe you start the message goes the other way that sends the knowledge of the recipient.
You don't really have. I mean, you don't need that,
Just
right?
to get things going. You just might need to send more stuff.
Yeah. If I just multicast out all the updates I've made periodically, then it would work fine. And if it's unreliable multicast, then you periodically do a real full-fledged sync to fill in the holes of stuff you've missed.
Right.
That would
actually think about that.
So it's a cute property. We guarantee convergence as long as your topology is well connected. Even if you have conflict resolution handlers at different replicas that do different things, we still guarantee convergence because of the fact that the resolutions propagate everywhere. Assuming we deal with this fighting resolution resolver problem. And we guarantee that we detect all conflicts, which is unlike some replication systems in Microsoft. And the interesting thing is we support both manual and automatic resolution, and you can mix and match. Right? You don't have to have all automatic resolution. We don't assume that everything's automatically resolved. So if you have certain types of items for which automatic resolution makes sense, you can use that. If you have other items for which manual resolution is the only thing that really makes sense, you can do that. And you can support both in the same system.
In this approach, can you sort of minimize the potential for conflict by scheduling things like trying to do all your replicas at once?
Right. So if you in fact want to layer some sort of locking protocol or something like that on top of this, that's fine. We don't really care. So you can do any sort of conflict avoidance mechanism on top of this that you want. We only have to make sure that we deal with conflicts if they actually happen. Yeah.
You compare this down with the loop techniques?
No, not explicitly. So that's basically the end of the talk, people. So my conclusion is I think we've done a pretty good job of meeting all of the requirements for this wide class of applications. We've come up with a protocol that's fairly flexible. There's still different ways of using the protocol, and reasonably scalable and robust for a wide variety of situations. And so it'd be interesting to see how this actually gets used in the applications that are being built on it. So I'll end there.